Melissa Reidy.
I'm Archita Bhattacharyya, and today with us is our next podcast guest, Daren Gooddy. Professor Daren Gooddy is a hydro-geochemist with over 30 years of experience as a groundwater processes team leader in British Geological Survey. He's now currently working with the UK Centre of Ecology and Hydrology. His most notable research encompasses nutrient cycling in groundwater, effects of agrochemical on water quality, and using tracers to track water movement and hydrogeological processes. Welcome, Daren. We are very pleased to have you.
Thank you. Well, nice to be here.
Daren, your research looks at how agricultural chemicals have changed in the particular, the nitrogen, the carbon, and the phosphorus cycles in water systems. But overall, why should anyone be concerned about these changes?
Well, I suppose one of the key things that motivated my research a number of years ago was the impact of nitrogen on ecosystems. But the original interest in nitrogen came from what was perceived to be a sort of a human health issue and what people often termed blue baby syndrome or methemoglobinemia. It sort of transpires that that's really a very, very rare occurrence. And it's actually quite hard to relate that back to nitrate pollution. So my interest sort of in this came more from the perspective of understanding the impact of nitrogen and other nutrients on ecosystems. And that's really why we should be concerned about increasing amounts of NP and to a lesser extent carbon perhaps, although it's more of the pollutant aspects of microcarbon compounds that are more of concern. But that's why we need to be concerned because of the impact on ecosystems. Of course, this has come somewhat full circle now. And having said for years that I didn't think that nitrogen in particular was a particularly a human concern, a number of publications have come out over the last 5 or 10 years, which have started to suggest that high concentration of nitrate in your diet can actually cause all kinds of cancers. So it's actually a current part of our new research going forward, working with King's College London to try and understand if there are some associated health risks with increasing nutrients in the water cycle. But overall, the biggest problem is that we're increasing the amount of nutrients that are getting into our ecosystems and we're perturbing the natural system. And this ends up leading to, for example, in surface water systems, algal blooms, which then ultimately take the oxygen out of the water and kill fish populations.
Are you looking mostly at like groundwater entering surface water systems, or are you looking at sort of downstream effects as well?
So I suppose one of the things about throughout my career is that I've always thought that the rocks rather get in the way. So I suppose I'm perhaps more interested in the water, and I suppose I'm a water chemist. I don't really know any boundaries. I'm not too bothered about whether the water's underground or the water's in a sort of surface water environment. I am interested and have been interested in that sort of zone of interface between surface waters and groundwaters, because that generally is where a lot of sort of interesting biogeochemistry takes place, when you've got that sort of movement from one sort of relatively oxygen depleted environment sometimes into an oxygen rich environment, often going through a sort of intermediate zone, which is a real hotspot for microactivity. Do I go further downstream than that? So no, I'm interested in groundwater. I'm interested in groundwater surface water interaction, and increasingly over the years, I've done more surface water work. But I've never really followed things down through to the estuary up until now, which is currently in my new role at UKCEH, starting to do some more work looking at how pollutants disperse as they get further and further down the river network.
You mentioned pollutants. Are there any other chemicals of concern that are getting into groundwater or that are emerging as particularly problematic for moving from land into groundwater?
So the interesting thing with organic chemistry, really, and analysing organic compounds is our knowledge and our fear is very much driven by the analytical capabilities of the time. So the more we can analyse and the lower concentrations we can reach, the more things we have to be concerned about, which is the triumph for analytical chemistry and our ability to measure lower and lower concentrations of things. You get to a point where you find huge amounts, or at least a small amount of everything, in your water sample, because you can just measure it at such incredibly low concentrations. I think there's still major concerns around a number of the principal organic contaminants of groundwater that there have been for a number of years, which is still around pesticides. If we're to concern ourselves with other organic compounds and the so-called emerging organic compounds, although, it's a strange expression because many of them have already emerged, they're already there. Currently, there's quite a lot of concern around PFAS in the environment and these so-called forever chemicals that never go away. They're a concern. There's an awful lot of them. They don't seem to break down very much. And we're not really very sure about what really happens to the environment and how far they're transported. And I guess even more so, we're not really sure about the long-term ecological effects of PFAS in the environment. So yeah, I think that's perhaps one to watch in the future. But most of these emerging organic contaminants are just very good tracers of anthropogenic activity, and they're a very good marker for understanding where humans have been and where they haven't been.
Because a large part of your work is involving tracers to track groundwater movement, for the listeners of this podcast who aren't familiar with tracers, can you simplify that and give us a quick explanation about how you use them to track groundwater movement?
Yeah, so I guess you could break tracers down into two broad categories, and one of which would be something that is qualitative. So that's, as I just mentioned, being able to detect an emerging organic compound. You know it's been produced at a certain point in history. And if you find it, you know that your water has components from that time in history. And then, of course, you can do the quantitative approach. And that's using compounds such as chlorofluorocarbons and sulfur hexafluoride. And really what we're interested in is giving us a much more accurate measurement of how old our water is. And then again, you can trace this down into much finer resolution, so that I've been interested in waters that are around about 50 to 60 years old, which in terms of sort of a standard water cycle in a well-developed Western country, which has a developed groundwater system, that's the kind of residence time you'd expect to see, which is why we focused on that. But if you were to go into older systems and where the water's much less exploited, then you need to use other tracers, and tracers which have a much greater age range. So you could look at your 14 carbon tracer, which will give you waters between 30 and 50,000 years old. I suppose the skill with tracers is to know which one to use in your environment. And if you're going into your environment cold, then you need to use, a broad spectrum of them to try and understand what's going on. But most of my career has been about really understanding how things go from A to B and what happens to them along the way. And I guess tracers are just a way of understanding how long it takes a water particle or a water molecule to go from one place to another, whether that's in groundwater or surface water. And the value of that is obviously if you have some contaminant incident, you can quite clearly work out how long it's going to take to get from point A to point B. And hopefully you might even be able to do something about it.
Keeping sort of the theme of a simple explanation for those listeners who might not be familiar with this, how do agrochemicals enter groundwater from the agricultural landscape or the terrestrial landscape?
Well, it very much depends on the environment that you're in or the particular geological setting that you're in. So, for example, if we take the United Kingdom, we have, I guess, what we call three main geologies. One, we're fractured, so water will travel from the surface when it rains, move quite rapidly through cracks in the soil and the rocks, and reach groundwater really quite quickly. Tracers can tell you that. And then if we have the other main aquifer in the UK, the sandstone, but this is mainly a porous aquifer, so think of a sand, so sort of pore spaces. Rainwater lands on the surface, percolates through the soil, wets it up, and moves in a much more uniform manner, hopefully, through your unsaturated zone. That's where you don't have 100% water saturation, slowly down onto your water table. And then we have a third option, which is a kind of a combination of the two, where we have a slightly fractured medium, which also has some porous rock as well. And that's where it becomes a little bit more complicated because you've got this partitioning of the water moving between fractures and the pore space. And that has implications for how fast your water moves down through the unsaturated zone to the water table, and also how quickly different contaminants respond to rainfall. And that's an important point to muse over because, for example, nitrate and pesticides, they don't travel through the unsaturated zone to the water table in the same way because they have different mechanisms. So if you want to understand how contaminants move from the surface to the subsurface, you have to look at them. You can't just look at one tracer to understand how that particular contaminant is going to move, because it won't necessarily move like a water molecule.
How much do we know about the consequences of these agrochemicals accumulating in groundwater? What are the flow-on effects of that? And do you have some examples?
That's an interesting question. The impacts of excessive amounts of nutrients getting into your groundwater system, to start with, is that ultimately this either gets into the drinking water supply and we drink it, and as I alluded to previously, this may have an impact on human health. It may not. It's still yet to be determined. And then also, most nitrate that gets into the groundwater system, it generally takes quite a long time, but eventually that water will end up most likely in a river, or if you're nearer to the coast, it'll end up submarine groundwater decharge. The impact of excess nitrogen is that you propagate such things as algal blooms as you're adding to an already nitrogen and phosphorus-rich environment, particularly in surface waters. With pesticides, one of the real problems with pesticides is as much as a broad spectrum pesticide that's applied to agricultural land doesn't just target what you've intended the pesticide to eradicate. Once it's in your groundwater system and eventually comes into your river system, you're also then potentially affecting non-target organisms. So in fact, organisms that were never intended to be anywhere near that organic compound, and particularly non-target organisms which are higher up the food chain.
You've studied the impact of climate change on nutrient cycles. So can you tell us how climate change might alter global nutrient cycles within groundwater?
Globally, that's very challenging because climate change will have different impacts on different parts of the globe differently. The classic for the UK, and I'm going to stick with the UK for now, is that we expect warmer, wetter winters. And this means that there's going to be a change in recharge patterns. So it's going to changes when it rains. And I think most people would probably agree that we already can see these sort of changes in our climatic system, as you alluded to with your question. That's important because we're going to get many more extremes. We're going to get more droughts, and we're going to get more floods. So that actually makes predicting what's going to happen to what I will call legacy contaminants. That's everything that we think of that's already in the unsaturated zone. So I'm going to stick with nitrate because nitrate's is relatively easy to use an example here. So nitrate in the unsaturated zone, what's going to happen to that under a changing climate? Well, it very much depends if you have, more intense rainfall. And that has two effects. One is because more intense rainfall means that actually your nitrate is going to move faster. So potentially, we're going to get this unsaturated zone nitrate, which may have been, taking 50 years to move through the unsaturated zone before it gets to the water table, potentially going to move much more quickly. But actually, if you get much higher rainfall, it's also going to be much more dilute. But the net flux is still the same. So the same amount of nitrogen comes through. So what does climate change mean? Well, it means the water cycle is going to change, but it's going to change in a slightly unpredictable way. So yes, it is likely that things will move forward rapidly, but it might be in a much more stop-start manner, because as I also said, we're more likely to have more droughts. And if you've got more droughts, there's very little movement through the unsaturated zone in particular. And what do droughts also mean in terms of groundwater feeding surface water streams? Well, I guess the potential is that if it's a very highly dependent stream on groundwater, and in the south of England where I am, for example, a lot of the streams, have what we call a base flow index of around about 90%. That means 90% of the flow is made up from groundwater. If that flow regime is significantly disrupted, it means that there's going to be no stream anymore over the summer months, because the groundwater table is depleted so much. And that means that everything that should have been in that river isn't going to be there anymore. So it could really have quite dramatic impacts on ecosystems because there's just not enough water. And the flip side of that, of course, is the flood side of it, whereby we're getting far too much water coming through our systems and leading to elevated groundwater and consequently greater discharge into rivers. And the longer that you have that elevated groundwater level, the longer your flood conditions are going to continue, because that flood finds it harder and harder to dissipate because there's nowhere for that water to go. So what does that mean for nutrients? Well, it probably means that nutrient cycles will perhaps, I would say, and I'll stick my neck out for this, will sort of speed up. That's more of a sort of an immediate thing over the next sort of 20 to 30 years. And then going forward after that, I guess it's much harder to predict what will happen. We also have to factor in what does climate change mean for temperature, and higher temperatures generally mean greater biogeochemical activity. So we could expect to see more natural processing nitrate. So we might see that nitrate in our soils under higher temperatures and perhaps more favourable humidity conditions, we see much more denitrification. So we see a greater removal of nitrate before it gets into our groundwater. This could be a positive. The downside of greater denitrification in the soil, of course, is that you produce more nitrous oxide, which is a greenhouse gas. The impacts of climate change on nutrients and on the whole water system is quite complex, and there are a number of feedbacks.
It just, from my perspective, sounds like this is an incredibly multidisciplinary approach that's required to answer these questions.
Yeah, I think I would agree with you. You need to pull in other disciplines, and I think that's really key. We need to be interdisciplinary in the way that we look at things. You don't want to be thought of as being the groundwater guy or the surface water girl. You want to be part of a team. You don't want to be pigeonholed. You want to be part of that whole team. And actually, this is one of the key things about PhDs. Really, is that you don't really have a PhD in, or very rarely in environmental science, do you have a PhD in a subject. I haven't got a PhD in chemistry. And that's because, and that's one of the good things about a PhD, is that you get this, often you get this multidisciplinary training. So you do have, something at its core. It might be hydrogeology, subsurface hydrology, but you're going to bring in all of these other things around it. And that's what we need going forward, is we need these sort of multidisciplinary scientists who have some specialities and knowledge of the periphery areas, but also they can then work with people who have more speciality in those periphery areas. And the key is, and one of the biggest challenges always for scientists, is the ability to be able to talk between disciplines, because people speak a different language, and they can, I might speak to an American and say the unsaturated zone, and they'll look at me blankly because they'll be saying, what's this? And you'll go, okay, it's the Beidou zone. And that's just an example in groundwater. But even between hydrology and groundwater studies, there is a difference in terminology. And then you talk about people who do, microbiology and biogeochemical cycling, and they've got slightly different terminology. And really, having somebody who is a universal translator and being able to work together in these teams is extremely valuable. And that's really one of the biggest challenges we have often when we have these interdisciplinary groups together, is making sure that we really understand what everyone's saying.
So we're going to switch to you as a person and a researcher now quickly. What overall sparked your interest in the career that you've had, the topics that you've explored?
Well, I like solving problems, I suppose. I developed the facility to do residence time indicators, actually with George Darling. I couldn't have done it without him. But that was because there was a need to solve a problem, not because I have a particular interest in residence time indicators. And similarly, the work on phosphate that I've done and developing the method for phosphate oxygen isotopes, that came out of a project we were working on. We just didn't know where the phosphate came from. And I said, well, maybe the isotopes will tell us. And then we realized nobody could really measure the isotopes of phosphate. So we went off and set about, developing a method of doing that, and got a grant and got it funded. So the thing that interests me, and I suppose most of my career has been about, I'll use the term glibly, making up methods or adapting methods and combining methods together. Again, looking how things go from A to B and what happens to them along the way. That's what sparks me. That's what interests me. Trying to understand how systems work, and trying to use the methods that we have and tweak them, develop them. I guess I get, don't try and develop a method. It's absolutely awful. It's just the worst period of your life. It just doesn't work, and then it doesn't work, and then it doesn't work, and just when you're about to despair and give up, it doesn't work again. So eventually you get there, but it's extremely hard work developing methods. So don't take it on lightly. Yeah, that's what sparks me. It's trying to understand processes, I suppose. And so most of the methods I've developed have all been about trying to understand the processes that are happening. Because hey, I want to find out something that nobody else knows, and I think that's one of the keys for all people who do research. They've got this little hook. I'd like to know something that nobody else has worked out before. Well, that's kind of quite cool. That's the hook for me. I might find a little bit self-centered and egocentric, but actually, no, that's what I want to do. I want to find something out that nobody else knows, and then I want to tell them about it.
Good answer. So in your view, what's been one of the biggest breakthroughs in hydrological research in the last 10 years, and what do you think are going to be the big trends and breakthroughs that we'll see in the next 10 years or so?
That's the how to make myself rich question. So if I really knew the answer, I wouldn't tell you. But I think one of the issues that came up around about 25 years, 30 years ago, and I was at a conference, International Association of Hydrogeologists conference, I think it was actually. And I sat down and had lunch with a guy, and I think he was from the United States, and his name escapes me. And he said, the next big thing in hydrogeology is going to be microbiology, geomicrobiology. It's going to be the next big thing. It's going to turn it all around. Anyway, it went a bit quiet for the next 25 years or so, and nobody was really doing anything. But I think that there's an awful lot that we need to do in terms of understanding what happens in the subsurface with the microbial communities. It's a huge biomass, and we know very little about it. And I think, potentially the fact that we've started to learn something about it is one of the sort of biggest changes that we've had in recent years, I'd say, in sort of understanding groundwater science. And then going forward, I'm going to extend that, and I'd say, it's probably going to be the next kind of state. So a lot of the microbial work, which has been, starting to really take off, has been facilitated by quantitative PCR, polymerase chain reactions. And so I'm kind of going to go down that front for the next 10 years, and the kind of eDNA sort of techniques and things, I think those are going to be really, really important. I think groundwater is a very mature science, which is to say that, a lot of it moves well, both literally and metaphorically, moves quite slowly. There aren't really step change change
Great
breakthroughs.
joke.
Thank you. I hadn't even rehearsed that one, which is unusual. So so things don't move particularly quickly in groundwater. There's no paradigm shift in the way we do things. I think in the last, and it's probably more than 10 years, the focus on the groundwater surface water interaction side of things has been really important. So I'm a chemist, and obviously, so I started my career looking at organic carbon in groundwater, and the answer between 1 and 3 generally. I mean, I spent about 5 years doing that, and it came a little bit dull. So when the opportunity came to sort of work in an environment where the organic carbon actually did something, because a lot of organic carbon in our groundwater systems is highly recalcitrant, it's very old, doesn't really do anything, nobody wants to eat it, no one wants to do anything with it, just sits around. So when it came to the opportunity to work in groundwater surface water environments where you have these hot spots where things are actually happening, I think it's a much more dynamic area of science, and understanding the link between groundwater and surface water and understanding the biogeochemical links, I think, is really important. And I think that's something that we've done in the last 15, 20 years or so. We've got much better at sort of doing that sort of thing. Groundwater surface water interaction didn't really exist when I started work for the Geological Survey 30 plus years ago.
Our last question, for the early career scientists who are listening, could you share the best and worst piece of career advice you've ever received, or that you can think of right now?
The best piece of career advice I ever received, and I may have said this to 1 or 2 of my PhD students, is if you're going to write a paper, make sure it's useful. Now, okay, that's what is useful. I guess the proof is always in the pudding, and does anyone else cite it? But yeah, make sure it's useful. And also, in the abstract, make sure you include some numbers, okay?
Yes, so my supervisor said that to me too.
Well, there we go.
It's great advice.
But in terms of bad scientific advice, that's a very difficult question, because I think if it was bad advice, I might have either forgotten it or ignored it, or I'm not sure. I'm not sure I'd say they have had particularly bad advice.
Thanks so much for listening to HydroTalks. A big thank you to Daren Gooddy for his time today, for talking all things hydrology with us, and we will see you during the next episode of the HydroTalks podcast.